Yeah, very nearly at 400, yes. Good point, Jackson. And hello, Lex, as well. Yes, good morning, everyone. Welcome to Physics with Keith. For those who don't know me, my name is Keith. I'm a physics teacher based somewhere in the south of Essex. And I've been offering these free online tuition sessions since pretty much the start of the pandemic to support people with their physics education. And this week's session is all about radioactivity. Now, this week's session is going to be focused on A-level physics. So if you're a GCSE student, see how well you can keep up. There's a lot going on. It's not going to be straightforward. Certainly, the mathematics will be a step further than you're used to, be a little bit more complicated than you're used to dealing with. But I'm hoping you'll be able to follow it anyway. You will need a scientific calculator. And what I'll say as well, before I switch over and start, is if this is your first time, if you're new to Physics with Keith, you don't know how this works, you'll see there's a little chat thing appearing, which side is it? This side, down here on the screen, and you can communicate with me and with everyone else through YouTube chat. The second way that you can communicate with me, which is to send answers through to me, is via Spiral, which is a free service that I've been using. This is not a paid for promotion. I don't get paid by Spiral for this or anything, but I've just popped a link into the chat. If you click that link, you don't need to, yes, Wombat. This is usually taught in year 13, although it does depend on your school, and the order that things are taught in also depends on how your school chooses to progress through the scheme of work. So there are differences, but in my school, we tend to cover it in year 13. It's a bit more advanced. It involves mathematics that takes you a little bit beyond what you're used to in year 12. Although not too far. It's not too bad. GCSE students can keep up. So anyway, if you click that Spiral, other side, click that Spiral link. It doesn't matter what you name yourself, because I'm really not looking at the names. And that way you can give me answers that will be anonymous. And maybe we can share some answers, but your name won't be attached to them. So that's one way that you can allow yourself to make mistakes with no consequences. It doesn't matter. At the moment, if you do click that Spiral link, it won't allow you to type an answer, because I've not asked a question yet, so that's why. Okay, so I'm going to switch across now and start on today's session. There it is. Just make sure I've got the correct window on top. There we go. So, more radioactivity, and mainly because a few of you were desperate for it, I did spend about an hour this morning going through and putting silly pictures into this PowerPoint presentation. I don't know where they've come from. They're websites that offer free, royalty-free for private and commercial use cartoons. These are apparently, most of these are from a computer game, but this is a game I've not played. I don't play computer games. That's far too childish. I do. Okay, so this is what we're looking at today. We're going to derive the equation, or two equations, for radioactive decay. That's the first thing we're going to do. The second thing we're going to do is use that equation. And I've written a question generator just this morning, actually. So it's a little bit rough around the edges, but I made a question generator so we can get a bit of practice using the equation. For GCSE students, this is going to be... It's too late, Wombat. The die is cast. No, so the... I forgot what I was going to say now. The question generator is so we can get a bit more practice. So if you're a GCSE student, there's no reason why you can't work through these drills as we do them and get better and better at doing these calculations. You might want to go on to do A-level physics. You might not. But all practice with arithmetic on a calculator is good practice. So don't worry about that. And the last thing I want to do is have a look at some graphs. That's going to be tricky to do on the screen, asking you to answer questions about graphs on a screen. That's going to be tricky, but we'll see how that goes, if we've got time for it. If not, I'll just show you how to use these graphs. Not in the GCSE way, but in a more rigorous, robust A-level way. Okay, so this little thing here reminds me that I have to switch across now to OneNote so I can do the derivation on paper. My satisfaction is immeasurable and my day is saved. I don't understand, Pranav. You are far too what's the word there? Well read, far too literate, or I don't know. Cultured. You're far more cultured than me if that's a reference to something, because I don't know it. Okay, so here we go. Deriving the equation. First things first. If we have radioactive decay, then what we are saying is that unstable precocious. I'm not precocious. It's all right, Pranav. I didn't make them. I need to focus. Right, the radioactive decay. The principle of radioactive decay is that every unstable nucleus has a probability of decaying. And for a particular isotope, the probability of a nucleus decaying is the same for every nucleus, which means we can never predict exactly when a nucleus will decay. And we can never predict which nucleus from a sample will decay next. But what we do know is that they all have the same chance of decaying, which means in some interval of time, if I've got more of these nuclei, then I can expect in that interval of time more of them to decay. And if I have fewer of those nuclei, then I can expect fewer of them to decay. Because there's fewer of them left, and each one has the same chance of decaying, I'm going to get fewer decays in the next time interval. So that's a sort of a principle. The amount of radioactive nuclei that we have at any point in time, I'm going to call n. And I'm going to say that the rate at which these nuclei decay, I'm going to call the activity. And I can represent that as a change in the number of radioactive nuclei I have, divided by some interval in time. Okay. And that's our activity. So I could put a little a before this and say that's my activity, but it doesn't really matter. I can talk about activity another time. And we just said that if I have more nuclei, this activity, the rate of decay, will be higher, which means this thing here is proportional to n. Well, in fact, it's not proportional to n because we have a reduction. This is a reduction in number. So I could put a minus before here, or I could put a minus here. I'll put a minus there, I think. Let's get rid of this a. I don't need that. So the rate of decay is proportional to the number, but actually it's minus because it's a decay. So this amount keeps getting smaller and smaller and smaller as this gets smaller, but it's a reduction. So that's where that minus comes from. In fact, I am bothered about putting the minus there. So I'm going to put the minus here. It's a negative rate of change. It's a reduction. Okay. Let's turn this thing into an equation. So with any sort of proportionality, we can turn it into an equation by including a constant of proportionality. And in radioactive decay, it is traditional to use a lambda. I could use a k, I could use a c for a constant, I could use anything I like, but we tend to use a lambda for this constant of proportionality. One second, I just have to restart my tablet because it's been playing up. There we go. So, good morning, Ted. So our constant of proportionality, I'm calling lambda. So our expression now looks like this, with minus lambda as this constant. Now, if I take these to the limit, these small intervals of time to the limit where the interval of time is 0, then I can rewrite this like this. Oh, it's gone down again. Let's just restart it again. It's not coming back online. Stand by. There we go. I need to buy a new graphics tablet, really, but I can't afford it, so I'm having to make do with this one, which I have to keep restarting. Now, if you're really interested in this calculus business, in what it means to move from a delta to a D, I've recorded a whole series of videos all about calculus. Maybe I'll put a link in the description for anyone that's watching this back later, but everyone else, just search for through my channel for the playlists, and there's a playlist there all about calculus, which you might enjoy. It's where physics starts getting real. I'm going to rearrange this. I'm going to gather all my terms that are similar. So I'm going to put my n's to the left and my dt's to the right, and I end up with 1 over n. It's all right. You don't need to apologize, Ted. This isn't compulsory. Not like school, where you have to attend. Of course, you don't have to attend school, do you? Because there is always the option to be homeschooled. So there we go. We have this 1 over n dn equals minus lambda dt. So I've just rearranged that equation. And now is the clever bit. I add up all these little chunks. So A-level students are thinking, oh, yes, I might have seen this before when deriving the expression for the decay, for the reduction of the charge on, yeah, Jackson, there's plenty of people who don't. So the reduction of charge on a capacitor. It's the same sort of derivation. You might have seen this sort of derivation for how the amplitude of a harmonic oscillator reduces if the oscillator is lightly damped. Or think of another example. The popular other example is cooling. Yep. So I mean, that's at least two of you. I mean, I knew about YouTube, but there were maybe others out there as well. There are benefits of school. There are drawbacks to school. There are benefits of homeschool. There are drawbacks of homeschool. I'm not going to go into the debate in this video. I'll let you do that later if you want. So what I'm going to do is I'm going to sum over all of those small intervals. Being fussy and trying to line up my S's. That's just a sum. That's all we're doing. Adding up all those small little chunks. And for reasons that I will not go into in this video, because I've forgotten, but I did record as part of my video series about calculus the reason why, when you integrate 1 over n, you get the natural log of n. And I've forgotten why. This is why I recorded videos about things. I have such a poor memory. And you get a constant of proportionality, which, a constant of integration, which I'm not going to write down here. I'll just write it at the end. And integrating, oh yeah, just, the thing is, I want them to look perfect, and they're never quite there, are they, Pranav? So, adding up, oh, hi Aaron Deeps, good to see you. So adding up my, oh, that was a dodgy lambda as well. Can get better than that. Right, adding up all those little time intervals, you get this. Now, if that step is complete mystery to you, as I said before, 12-part series, it's about 2 hours long, that I recorded about calculus. Please go ahead and watch it later and you'll get some insight into this step. The good news is that that step, you don't have to understand why that works in A-level physics. You should know that it works. You should know about it. So I've recorded that as part of a video. Anyway, here we go with this expression here. Now, laws of logs. Which some of you will be familiar with. Laws of logs. The inverse function to a natural log is to raise something to the power of e. Which the maths department, I think, are going to get upset with me if I refer to that as exponentializing or something. But that's what I'm going to do anyway. So I'm going to raise e to the power of this equation. So e to the power of the natural log of n is going to equal e to the power of minus lambda t plus c. Now, these are inverse functions, so that leaves me with n equals. If I've lost you, by the way, don't worry, we're just deriving the equation at the moment. We're going to use the equation in a bit. So if I've lost you, just stick with it. I'll give you the equation. This part here, right, I've got the same base, and I'm adding the two exponents. So this is exactly the same as minus lambda t e to the c, just like that. It means the same thing. That's one of the various laws of logs that you learn. Now, what does this equal when t equals 0? When t is equal to 0, this term here is equal to 1. So when t is equal to 0, n is equal to ec. C was a constant, so e to the power of c is a constant. So I'm going to rename that constant N0, the number of radioactive nuclei when the time was 0, so at the start, I'm going to call N0. Now I can plug that back into this equation, and we end up with N equals N0 e to the minus lambda t. Groovy. That's the first equation. Just going to highlight it. And we'll be using it. Oops, get the highlighter pen out. We're going to be using this a bit later, so do make a note of that equation. Lambda was that constant, that decay constant. T was how long since you measured N0 the radioactive source has been decaying for. And N0 is how many of the radioactive nuclei there were originally. N is how many we've got after a time t. Now, a couple of things to be aware of. If t is measured in seconds, then lambda has to be measured in units of per second, 1/2. If t is measured in years, lambda has to be measured in per year, 1/year. And sometimes I'll use the symbol y for a year. Sometimes I'll use YR for a year. Today I've decided to be a bit different, and my symbol for a year is A from annus, from year. So I've used A and A to the -1 to mean year. It is a standard convention. D for day, A for year, that sort of thing. So that's the first thing. This thing up here has to be, for A-level students, we'll say dimensionless. So it has no dimensions. And so you can raise e to the power of a dimensionless quantity. Now, I need to get to the bottom of what this quantity lambda really means. So let's figure that out. First of all, I'm going to divide through by N0. We're nearly finished. If you're glazing over, we're nearly finished. That was the first equation. There are only two I wanted to derive. That's e to the minus lambda t. Now, I want to get rid of that e. I want lambda as the subject because I want to work out what lambda is. So I'm going to raise all this to the... I'm going to take the natural logarithm of all this. I'm going to do that function. So natural log of n/n0 is going to equal minus lambda t. Remember, e and natural log are inverse functions. Okay, I'm getting closer. I still don't quite know what lambda is because of this thing here. So what we're going to do is we're going to take a particular case. Let's say that when the time is equal to the half-life, that's a t with a subscript a half, that's how long it takes for half of the radioactive nuclei to decay, then we'll know that n/n0 will be equal to a half. Oops. Shouldn't have an equals there. Okay. The proportion of radioactive nuclei we have left is 50%. The bottom number is double the top number. We end up with a half. Okay. So now we can plug that into this equation here, and we end up with natural log of a half equals minus lambda t. You might look at that and think, well, natural log of a half, what's that then? Well, that's the same as the natural log of 1 minus the natural log of 2. That's one of the laws of logs. And I'm going to record a video all about those laws of logs. I haven't done it yet, but I do want to. Well, the natural log of 1 is 0. What do you raise the base e to the power of in order to get the value 1? 0. So this value here is 0. So we're just left with minus natural log of 2 equals minus lambda t. And of course, we can multiply through by -1. So we have natural log of 2 equals lambda t. But this is not just any old t. This is the half-life. So I should probably put a subscript half on all of these t's. And so finally, we now know what lambda is. Lambda is the natural log of 2 divided by the half-life. It's actually the probability of decay. So let's just highlight that because that's our second equation. We're going to be dealing with decay constants, lambdas, and we're going to be dealing with half-life. So we need to be able to convert between the two. This is how you do it. And you're going to get some practice in just a moment. So those two equations again, See if I can zoom out, or as I say, I call it in class, de-bigger it. There we are. I don't know whether that's too pixelated or whether you can see that okay. But those are the two equations that we're going to be using. Are there any questions before we move on to the questions? Type them into the chat. And if you haven't done so yet, click the spiral link. Give yourself any name you like. I don't really care what the name is. So you can give me the answers to the next few questions that are about to come up. Any questions before I move on? I'm going to give you 7 Mississippis. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi. Okay. We've had our 7 Mississippis. That's plenty. So let's switch back to the PowerPoint. And I'm going to want you to answer some... Let's just move this across there and check how many people are on Spiral. Only 7 people have registered on the Spiral link. Okay, okay. So these are the questions I'm going to want you to answer. And the first one, you can type straight in. Just a quick conversion, a straight conversion. Can you calculate the decay constant? And I'm going to want the unit as well. Can you calculate the decay constant for carbon-14, which has a half-life of 5,730 years? That's what the A means. So type your answer into Spiral. And we'll see what you come up with. I really hope you wrote those equations down because I didn't include them on this slide. I need the unit as well. Do need the unit. Yeah, I need the unit as well. I've got answers coming in which are correct, but I do want that unit as well. I marked one correct then that's incorrect. I need the unit. So decay constant has a unit, and it's going to be really important in these calculations that you know what that unit is. And I will talk you through what you do on your calculator in a second. I understand that. We have a correct answer with units so far. 1 correct answer with units. So let's start with the numerical part, and then we'll look at the unit part. So the numerical part. I'll get my calculator out, and I'm going to type the natural log of 2. However you do that on your calculator. On your calculator, you'll probably have a button that says ln. Or it might have log with a little subscript e. But ln is the natural log. So you're going to type on your calculator probably natural log, then 2. Then I would chuck brackets around that because I'm never quite sure how your calculators handle orders of operations. My calculator, I know exactly how it works, so I don't have to use brackets on mine. But yours, I don't know. So I would always use brackets on yours. Open bracket, natural log of 2, close bracket, divided by, and then you would put in the half-life, which here is 5730. And divide, you divide them. So divided by that. And that gives you a number. And most of you are giving me the correct number there of 1.21 times 10 to the negative 4. Or some of you didn't put it in standard form. You wrote down 0.000, how many zeros? 0.0000, 1, 234, 0.000121 or something like that. That's okay. So that's the number, the unit. Remember what I said? If you have a half-life in years, then you have a decay constant in units of per year. That's years to the -1. If you have a half-life in seconds, then you have a decay constant in per second. That's seconds to the -1. A lot of you gave me the right answer, but you automatically gave your unit in seconds to the -1. Be careful of that, because in exams, you could get half-lives given in weeks, half-lives given in days, half-lives given in milliseconds. You know, it doesn't. You have to make sure you can handle the unit correctly. If you have a unit prefix like milli or nano or something like that, I would enter that in standard form instead. Yeah. So the answer I'll show you is that, but the unit is per year because the half-life is in years. So have a go at the second one. We had some difficulties with the first one, so have a go at the second one. It's the other way around now. We want the half-life of uranium-234, which is the lowest half-life, the least stable of the naturally occurring uranium isotopes. So you don't find much of it in nature because it's so unstable. So calculate the answer and then chuck it into Spiral. If the A for years is bothering you, then use a Y. It doesn't matter. I know what you mean. Okay, so one of you has got pretty much the right answer, but you need to check your rounding. Okay, now you need to count the number of decimal places, the number of zeros. Yeah, that's better. No, I'm still not happy with the rounding. Give you a few moments to get the answer. Good, that's better. A few of you still not giving me an answer yet, but let's work through it together. In fact, what I'll do is I'll put it in, I'll use OneNote and I'll show you the working for it. So let's switch it across. Draw. Let's use blue. So we're using this bottom equation here. The half-life is what we want. We were given a decay constant. This is for the second one. We were given a decay constant equal to 2.83 times 10 to the -6 per year. So we need to write our equation where the half-life, I don't know why I've written an A, the half-life is going to be equal to natural log of 2 divided by lambda. Now, if you look at this equation, it is a 3-term equation. So rearranging this equation to get there is a GCSE skill. So if you're playing along at home and you're not an A-level student, it's the sort of thing you can continue to practice. Then we plug our numbers in. This is just a number the calculator is going to tell us. 2.83 times 10 to the -6. Oops. Oh. Let's try and get that line there. So when I plug it into my calculator, 2.83 E6 minus divide, I get the number 244,928 blah, 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 blah. Well, in standard form, that would be 2.44928 times 10 to the power of 5. Just be careful that your 9s don't look like 4s. And that's the wrong number of significant figures. So I was given a number to 3 significant figures. So I have to give, it's supposed to be an S, significant figures. So I have to give my answer to 3 significant figures. So rounding that to 3 significant figures is that. And I need the unit. The unit here was per year, so the unit is years. So that's how we, and you type that into your calculator. I'd chuck brackets around this bit here to make sure my calculator doesn't do natural log of 2 divided by that. But that's how you solve it using your calculator. So let's move on to question 3 then, which is using the equation, the other equation that was on that list. A little bit more tricky now. And once you've got the answer, just tap your answer into Spiral. And if you're watching this and you're thinking, this is helpful, yeah, maybe not this topic, but maybe a different topic, but yeah, these sessions look like they could be helpful, then just go ahead and subscribe to the channel, and you'll get notifications when I go live and when I release videos. Yeah, so let's just explain with those symbols then. We've got polonium-210, not actually bothered what it is, but we are told polonium-210 has a half-life of 140 days. And I want to know how much is still there, what proportion is still there after a year. Well, the proportion is going to be the new number divided by the original number. Someone has given me the correct answer, but the number of significant figures is incorrect. Believe it or not. So I'm going to be fussy and say no. A few more people are going to try and give me the answer. What you're trying to calculate is what n divided by n0 is. Someone has got the correct answer now. If at any point you get questions, chuck them into the chat. Yes, so E is E to the power of something rather than times 10 to the power of something. That's a different notation. We actually use the same symbol, and that's why it can get complicated, Wombat. Now, what I'm going to do when I use the drill, I'll use another slightly different symbol for E to the power of something. But E in the equation that I showed you in the derivation is Euler's number. It's just a number. It's just a number. So E is equal to 2.71828. I'm reading it because I can't pretend to remember it. 2.7182818284590452353602874713526662 and so on and so on and so on. Okay, let's go through this one, and then you can have a go at the next one yourselves, because this one seems to be causing some problems. Let's just switch across. And I'm going to delete the working from the last. Oops, I'm going to delete the working from the last question to give myself a bit of room. But I want to show those equations still there on the left. Let's use blue again. Okay, so the information we had the fact it was polonium, although I'm not interested in that really. We've got the half-life. I'm going to write that down. a half-life was 140 days. And the amount of time after the initial measurement is 1 year. 1 year, which is, I'm going to say, equal to 365 days. I know it's not quite, but I'll leave that to the astronomy videos. So 365 days. And so my equation that I've got written over there, n equals n naught e to the power of minus lambda t, I can rearrange this to get n over n naught. That's the proportion that's left. The new number divided by the original number is the proportion of what's left. So now I can plug my numbers in. Well, not quite. I don't know what lambda equals. I can't plug it in. I need to calculate lambda first. So let's calculate lambda. Let's do it over here. Lambda was equal to natural log of 2 divided by the half-life. Oops. Natural log of 2 divided by, and the half-life was 140 days. Let's do everything in days. As long as this unit and this unit are the same, it's fine. So let's do it all in units of days. So I get my calculator out and I do 140 underneath natural log of 2. And I get, and check my numbers here because I do make mistakes. So 4.951. I'll give myself an extra couple of digits here. They're called guard digits in case any rounding errors crop up later. Times 10 to the negative 3. And the units are per day. Okay, because my half-life was in days, my unit for decay constant is in per day. This is how many, the probability of decay per day. Now I'm going to be able to plug that into this equation here. So I've got e to the power of minus 4.951 times 10 to the minus 3 times by the time. It says it's 365 days. I'll plug that into my calculator. So minus that multiplied by 365 e to the power of that. And I get 0.1641 blah blah blah, which is the same as, there's no units, it's a proportion, it's a number divided by a number. And so that's the same as 16.41%, but I was given numbers, one year was given as 1.0a, so that was a too significant figure number. So I have to round this to 16%. So there was a couple of steps in there. I didn't know what the decay constant was, so I couldn't plug it straight into my equation. I had to calculate what the decay constant was. Once I've got the decay constant, I can plug it into that equation. So I'm just going to check Spiral again and see how many people get the answer. A couple of people, some people still not there. Okay, so I've showed you the calculation. If you want to see it again, then just let me know, and I can always switch back to that screen. It's still there. Otherwise, I will move on to the... Yeah, probably, Jackson. Yeah, there are easier ways. I wanted to practice using this equation, but actually, you could just use the method that we looked at in the last video, the last week. Yeah, absolutely, Pranav, almost certainly. So last week we looked at an equation. Yeah, exactly. Last week we looked at an equation where the proportion that was remaining was equal to half to the power of the number of half-lives. And so you could work out the number of half-lives as a fraction here. Exactly, yeah. So have a look at the chat. Jackson's typing it in there. And then that gives you the same answer. Or you could do the way that I've showed you. So GCSE equation, nothing wrong with that. And remember that you could be asked that in GCSE, but here it is. You can also use that lovely A-level equation with derived, and you'll get the same answer. You should get the same answer. Just be careful that you've got the same units here. Okay, so what proportion of the technetium-99m, that's a metastable isotope of technetium, it will decay into technetium-99 through gamma emission. It's got a half-life of 6 hours. It's really useful for medicine, for nuclear medicine. And I want to know how much is going to be left a day later. So if I go to the hospital, they give me some technetium for some reason, how much is still going to be in my body? What proportion is still going to be in my body a day later? Type your answer into Spiral, please. Then you can use the GCSE equation from last time, or you can use the equation we've looked at today. Doesn't matter. It's all good. It's good. I see a few A-level students are coming in with the correct answer, which is reassuring. Try it both methods. Something interesting happens if you, well, depending on your calculator, something interesting can happen if you try the two different methods. Just check your significant figures there. Someone who's just entered it, I'm just going to send it back saying it's incorrect. The number's okay, it's just I need the number of significant figures to be correct. I wonder if any of you are involved in the Isaac Physics Masterclass next week. We had one last week on Saturday. Didn't have one this week on Saturday. We've got another one next week on Saturday, which I think is the Year 10 one. Someone's just put the answer to the previous question. So I don't know whether you're aware, we're now on the 4th question on this list. That was the answer to the previous one. Still waiting for answers from a few of you. You can use, with this one, you can use your GCSE equation from last week. If you're a GCSE student, you're out there and you're thinking, there's a lot of stuff in this A-level one, then just see if you can solve it with your GCSE knowledge. Syntax errors, interesting. Mine doesn't tend to give me syntax errors, it tends to give me complex numbers and stuff. What do I need to put in after calculating the constant you raised to? So on your calculator, you would type it, depending which method, if you've worked out how many half-lives and you're using that method from before, you'd do 0.5, then you'd press the button on your calculator, which depending on your calculator, it could either say X with a little box in the top right corner, or X to the power of Y, or Y to the power of X. Then you would type in the proportion, the ratio, so how many half-lives. So half to the power of how many half-lives, and that will tell you that proportion. Or you could use e to the power of, and then you do minus. Make sure the minus is there, otherwise it will give you a syntax error. The, well, mine won't. Mine will give me a complex number. So minus the decay constant, which you'll have to calculate. Okay, so what is that? So 6 hours underneath the natural log of 2. is that minus that. Oh, I see. Yeah. So you've now got that. So you need to do e to the power of that. Yeah. E to the power of that. Yeah. Well done. Okay, so just be a little bit careful. One person's given the answer, but they've written the decimal and then just put a percentage sign at the end. So when you make a percentage sign, which means divided by 100, that's what percent means. You've got to times the number by 100, so it's the same number. If I don't give a minus, it gives me the inverse of the proportion. Okay. I haven't tried it. Okay, so yeah, so a couple of people have given me the answer. A few people still working on it. What's fascinating about this one is, well, for a start, you can actually solve this one quite easily. There's 4 half-lives. There's 24 hours in a day, so 6, 12, 18, 24. So there's 4 half-lives. So after 1 half-life, there's a half. After 2 half-lives, there's a quarter. After 3 half-lives, there's an eighth. After 4 half-lives, there's a 16th. And 1/16. Oh, look at that. It's the same answer. So, so you can do it that way. Or you can use the equation from the GCSE session last week, and it gives you the same answer. Or you can do what we've just said about calculating the decay constant. Now, I'm going to do it again on my calculator, and I'll show you the issue. So I'm going to type in half-life of 6 hours. I'll do it all in hours. Reciprocal of that multiplied by natural log of 2. So I've got my decay constant there. Minus my decay constant multiplied by the number of hours, and then e to the power of that. And I've got my answer. And then if I look on my calculator screen, it shows the following. Let me write it down. So this is what my calculator gives me as the answer as a percentage if I use the A-level method. 6.249999999999999. Hang on, I need to go to the new line. And I'm not showing my screen. There we go. I keep going. 9. Oh, hang on, I've lost track. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 6%. I hope you can see it now, Pranav. Should be there. Now, why is that an issue? Well, you may think, well, that's obviously... Yeah, that's great. You may think to yourself, well, that's obviously, 6.25. Yeah, but I was rounding my answer to 2 significant figures, wasn't I? Yep, lots of 9s. So if I round my answer to 2 significant figures, it gives me a different answer. If I simply halve 4 times to 2 significant figures, I get 6.3%. My calculator, if I plug in the numbers, it gives me 6.2%. And it's because my calculator is so precise that it doesn't try to cut corners and round things too early that it's caused this problem. Every calculator, when you do an exponential function, gives you an approximation of the answer. Because the Euler's number, it goes on forever. Transcendental number, it goes on forever. So there's no exact answer my calculator can give me. And so if you use that method, check what it says on your calculator. If you use the method that I showed you today, just bear in mind it is an approximation. Even your calculator will not give you an absolute answer. It will give you an approximation. And it rounds differently. I liked that. That made me smile. Right, okay. We have got some time, so I'll show you the drill. I don't know if we're going to get some chance to practice the drill, but I'll show you the drill, and then you know where to get it. If you are a regular participant of these tuition sessions, then check the links in the description to this tutorial, and you'll see there is a Facebook group that's described as being for regular participants. They have free access to things like my question generator, which I'm now going to show you, and all sorts of question generators. There's loads of resources on that Facebook group that you can download freely. Absolutely loads of them. If you're not a regular participant, then feel free to contact me and I'll explain how you can get hold of those resources. And if you happen to be someone who I teach in my school, then you've got them on Teams. So you don't need to ask. They're all there. Okay, so let's show you this drill. Here it is. If I press F9, I get a different question. Press F9, I get a different question. Press F9, I get a different question. Each time there's one thing missing. Now what you can do is you can hide the half-life bit and practice using the equation without the half-life bit if you want to. Or you can keep the half-life bit there and try to solve it using different methods and see which one you're comfortable with. But you should be able to use all of them, because sometimes you'll get questions that you have to use this equation to solve. And as always, if you click answers, the missing number appears. The unit of lambda in all of these is per second. The unit for time in all of these is the second. And these are actual half-lives for these different particles. You know, the beryllium-15 nucleus, the fermium-241 nucleus, and so on. These are actual half-lives for these. So that drill, I'm not going to go through it now. I don't really have time to use it now, but that drill you can use to practice using this equation until you can get it right every time. Now, for some of you, you don't need it. You've got this. But for a lot of you that I saw the answers coming through on Spiral, there were still mistakes happening. So using something like this probably is not going to be a bad thing. And the next thing I wanted to show you was half-lives from graphs. Now at GCSE level, you calculate the half-life. Oops, let's get this in the middle. You calculate the half-life from a graph. I think that's okay. Get rid of that. You would calculate the half-life on the graph by looking at the number at the start, halving it, reading across, reading down. And that's fine. A-level, that's not good enough. If you want the decay constant, for example, I suppose you could work out the half-life using that very basic GCSE way and then do natural log of 2 divided by that half-life, but it's not good enough. So I'm going to show you a method now that you can use to measure the half-life and the decay constant from a graph. And I've seen this on exam mark schemes, so this is one of those that you do need to be able to do. That's bad. Let me take a screenshot, put it into, hello, put it into one. I missed the unit again. Put it into OneNote last time. Got it. And then I can draw on this. And I would say to you, play along at home, work out what the half-life is at home. But the problem is that means you're holding up a ruler against the screen and all the rest of it, and I don't know how good that's going to be. But no, if you do want to play along at home, I'm just going to turn Spiral back on. If you want to play along at home, then go ahead, chuck the answer into Spiral as soon as you've got it. But also, let me know what method you used. And if you did it in more than one method, then let me know. I'm interested to see how you did the calculation. So here we go. If we want to calculate the half-life, GCSE, you read off here, you halve it, you read across, you read down, that's the half-life. Decay constant, natural log of 2 divided by the half-life. Fine. What do we do at A level? Well, Let's just move this out of the way. I've always got too many windows open. We remember that d, in this case, the number that's decaying is a, so I'm going to call it a, by dt is equal to minus lambda a. That was way back at the beginning of that derivation. That means that lambda is equal to minus dA by dt all divided by a. This is really useful if we don't have the number at the start, for example, or there isn't a whole half-life shown on the scale. If this graph didn't extend far enough for you to be able to use that GCSE method, you couldn't see a whole half-life, then you wouldn't be able to use that GCSE method, and then you'll have to do this. So what you'll do is you will draw a tangent somewhere sensible. That there looks like a sensible place to draw my tangent because it crosses right through that line there. In fact, I'm going to do that, and I'm going to move this line in a second. Don't start panicking. There we go. I'm going to draw my tangent there. That's not a bad tangent. I can do better tangents, but that'll do. And I extend the line as far as I can. This perhaps is a little bit too steep. Let's make it a little bit more shallow. Okay, I think that's okay for it. Still not happy with it. The problem of being a bit of I am a perfectionist, believe it or not. Still not happy with that, but okay, that'll have to do. So you draw your tangent and you compute the gradient of your tangent. I'm going to do that here. I'm going to say that this goes all the way up to... I'm pushed for time, so 1, 2... Let's just say it's halfway between. Let's say it's 450. So 450 minus... Let's read it from the axis, 0, divided by... This is the gradient, by the way. And then I'm going to read the x-axis. Okay, I'm going to say 0.1, 0.05. What do you reckon? So I'll say halfway. So 0.625 maybe. Tell me if I'm wrong. Of course, the initial number, I've got this back to front, of course. The final number is 0. The initial number is 450, so that should be negative. But I'm not bothered. I know the gradient is going to be negative anyway when I put it into this equation, so I'm not bothered about that. 7, 0.65, 0.625. Probably a little bit more than that. Let's go with 0.63. It's an approximation. I'm trying to read off a scale which is a little bit big from a screen rather than a piece of paper, so I can't get a ruler and linearly interpolate. How about using that point 50? That one there? Or that one there? Yeah. That's not 50 though, is it? That's not 50. It's 20. But I could definitely use that one. Should we use that one instead? Yeah, I like that one. 20, and let's say this is... it's all right. We all do it. I do it too. 0.6 minus 0. Let's do that then. That's probably a bit more accurate. And let's calculate the gradient. Okay, I should have the top numbers the other way around to get minus. I wrote them, committed to it, and I've got it the wrong way around, but it doesn't matter. Pranav says everyone messes up. So my gradient's actually minus 716.6, blah, 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 blah. That's here, so I need minus that, and then divide it by A. So that's going to be 716.67 divided by, and A I can read off. A was this point here, which was 200. Yeah, so it's the gradient of the tangent at that point divided by what that point is. And that gives me my decay constant of let's call it 3.6. per minute, because it's minutes on the x-axis. And then if I want to find a half-life, I can do natural log of 2 divided by that to get the half-life. I'm just going to do that to see what it looks like. So natural log of 2 underneath that. It says 0.2-ish apparently is the half-life. That looks about right. 0.193 actually. But yeah, that looks like it's about right for a half-life. About there-ish. And then we go half again. Yeah, I think that's about right for the half-life. So where your graph is too shallow for you to be able to just read off the half-life in the way you would do at GCSE level, you can use this method. There are other methods, but this is the graphical method to determine the decay constant from an exponential decay. Take the gradient at a point, divide that gradient by, well, minus that gradient divided by the value on the y-axis where you took the tangent. There's your decay constant. I'm just going to switch back to here a little bit and check that the number checks out. As with all my drills, if you click answers at the bottom, it tells you the answer. 3.6, 3.58. Okay, I'm happy with that. It's what I thought it was. And if I press F9, you can see I can get cases come up. If I keep pressing it, one will come up. There we are. So can we see one half-life on that one? Yes, we can. But if I keep going, eventually I'll get a curve that's too shallow to be able to measure one half-life off it or something like that. And so you'll have to then use that method. And we're going to switch back to here. I'm just interested to see what people came up with on spiral. No answers. Oh, never mind. No answers. So I'll pop that drill. The drill has a few different parts on it, but I'll pop that drill. I think that drill's already on that Facebook group. And well, we've been at this for an hour now. We did a bit more radioactivity. You've had a bit more practice. Don't know how useful it was. A-level, it doesn't really get that much more tricky than you've just seen, to be honest with you. The next session's about nuclear physics, and that's going to be from a GCSE perspective. Going to keep it GCSE level as much as I can. Nuclear energy, I'll try and keep GCSE level as well. We don't, Wombats. It's just I used the wrong numbers. Very, very foolish of me. Let's just switch back to that. The gradient is the final point minus the initial point, but I did initial point minus final point on the top here. So I messed up my numbers. This should be the other way around, which means it's minus. But remember, by this definition, I want minus the gradient anyway. And that's why, let's write this down. There we are, that's better. And that's why lambda becomes minus that. Yeah, I just messed this up. These two should be the other way around, which gives me that minus number. No worries, Ted. No worries at all. Yeah, so going back to the summary. So next session is going to be GCSE nuclear physics. Nuclear energy, I'll keep at GCSE level as well. Thermonuclear reactors, mostly GCSE. I might introduce a little bit A-level, but mostly GCSE. So if you've managed to stick it out through all the A-level stuff we've done for the last 5 weeks or so, well done. Don't worry. The next load of sessions are for you. They're all for you, GCSE level. But of course, A-level students would still benefit. And this is my last plug for this. If you haven't yet subscribed, please do. I'm on 398 subscribers, which is great. I've done a poll recently on Facebook to find out what topics you want to be covered in season 4. But if I could do that poll on YouTube, then that would be better. I'd have a larger audience and more people would participate. It's all in one place. YouTube polls are better than Facebook polls. But I can't do YouTube polls yet because you need 1,000 subscribers to be able to do them. So share this with your friends, get them involved. If you find it helpful, you're going to want to share it with your friends. And I will see you next week. Stay safe. Have fun in school, those of you who are in school. And I'll see you next time. I'm going to hit the close button now.